Okay, welcome back. In this lecture and the next, I will introduce the topic of hypothesis testing, which will be a main focus of this course for the rest of the semester. A hypothesis is a prediction that is tested in a research study. More specifically, hypothesis testing is a systematic procedure for deciding whether the results of a research study, which examine a sample, support a hypothesis which applies to a population. So in this lecture, I'll review the core logic behind hypothesis testing, as well as the basic steps for testing a hypothesis. Before doing that, I always like to review concepts from the previous lectures, so I'll do that now. So here's a review from last time. In previous lectures, we've learned about z-scores, which describe the number of standard deviations a score is above or below the mean. We also learned that it's possible to manipulate the z-score formula to change a z-score back to the raw or original score. For any distribution of numbers, when converted to z-scores, the mean of the distribution of z-scores is 0, the standard deviation of 1, and the shape of the distribution will remain the same. We also learned about probability. Probabilities take on a range, and so when expressed as a proportion, a probability can range from 0 to 1, and when expressed as percentages, probability can range from 0 to 100. Probabilities are expressed as symbols. So for instance, we learned that we can express the probability of a coin landing on heads as 0.5. We can express that the probability is equal to something, or we can express a range like a probability is less than 0.05 or less than 5%. We also learned about the standard normal curve. The normal curve is a mathematical or theoretical distribution, and it has several important properties. As we can see from the picture, it's bell-shaped. It also is unimodal. That means that there is a single most frequent score, the mode, and in a normal curve, the mode is equal to the mean. That is, the average score is the most frequent score. The normal curve is also symmetrical around the mean. And exactly 50% of scores are above the mean and 50% of scores are below the mean. That also means that the mean is equal to the median. And then finally, there's a known percentage of scores above or below any point. As we can see here, 34% of scores fall between the mean and one standard deviation. That means that approximately 68% of the scores will fall between one standard deviation above and one standard deviation below the mean. We can also see that approximately 2% of the scores fall in the tails of the distribution either above 2 standard deviations or below 2 standard deviations, below the mean. Because the normal curve is a precise mathematical curve, it's also possible to determine the exact percentage of scores between any 2 points, which means that we can determine the exact percentage of scores in the distribution from the mean to a particular z-score, as well as from that z-score through the tail of the distribution. We do this by looking up the exact percentages in a lookup table. This is the lookup table that is found in the back of the textbook. We also learned about the distinction between populations and samples, and that there are specific symbols meant to express values from populations and samples. Symbols that are used to uh, that are used to symbolize values from populations are parameters, and they use Greek letters. Sample statistics are values from samples and are symbolized by Roman letters. All right, so let's begin with the new content for today, and this is an introduction to hypothesis testing. Let's start with some key terms. So first, a hypothesis is a prediction, often based on informal observation or previous research or theory, and we test that prediction in a research study. A theory is a set of principles that attempt to explain one or more facts, relationships, or events. Very often, psychologists develop specific hypotheses from theories. And then it's those hypotheses that are tested in research studies. Hypothesis testing is a systematic procedure for deciding whether the results of a research study, which examines a sample, supports a hypothesis which applies to a population. Hypothesis testing is the main tool of inferential statistics, in which statistics are used to make conclusions or inferences about populations. In this lecture, I'm going to follow the lead of the textbook authors and try to keep the introduction to hypothesis testing as simple as possible, which means that I'm not going to include some of the aspects of the process in this first lecture. So, specifically, psychological research in the real world involves a sample which has many individuals in it. However, I want to minimize what you have to learn at kind of in this one lecture. And so the examples that I'm going to use are about a study in which the sample only involves a single person. So the example that I'm going to use in this lecture is really quite unrealistic because it only involves a research study involving one person. Again, that's intentional, and this is so that you can learn the core logic and the steps of hypothesis testing before I add in some of the more complicated aspects of the process. So we're going to start slow and build a foundation. By the time you get to later chapters in the textbook and later lectures in this course, you'll actually learn the exact statistics that researchers use. But right now, I'm just going to prepare you to understand the hypothesis testing process. And so what you're going to see today is not what's actually used in real research. It's just to kind of give you the foundation so that when you do learn the real statistics, it's not too overwhelming. So I think the best way to learn hypothesis testing is to start with a very simple example. So that's what we're going to do here. Let's start by imagining that there's a psychology professor, and this professor has taught Psychology 101 for many semesters. At the end of every semester, the professor gives a final exam that covers everything that is taught in the course. The professor gives the same exam every semester, and therefore, after many years of giving the same exam and collecting all the test scores from a very large number of students, he's able to determine that the average grade on this exam is an 80, with a standard deviation of 7, and that the scores follow a normal distribution. And so that's what we see here. Now, although the scores on the final exam are pretty good, the professor is interested in determining how to help students learn and retain the course concepts even better. It just so happens that the professor has a friend who's an educational psychologist who's creating a training program to help students better retain information that they learn in college courses. Okay, so the professor has this friend who's designed this training program, and what the psychology professor decides to do is randomly select one student from the class and invites that student to participate in the training program as a way to test it out. While in the psychology class, the student is going to attend several sessions of the training program throughout the semester. So the question becomes, does this training program improve retention of the course material and therefore result in an improved exam performance? What we need to consider is what kind of a result from this very simple study of the one student would be the kind of result that the professor would need to conclude that the training program works. Ultimately, we have a hypothesis testing problem here. Because the professor wants to be able to draw a general conclusion about whether the training program improves retention of the course concepts and therefore results in better exam performance. The conclusion that the professor wants to make is ultimately meant to be about any student who could participate in the training. However, at the current time, the conclusion that the professor will be able to make will be based on the results of just studying this single student, this sample of this single trained student. There's a standard way that researchers approach any hypothesis testing problem, and for our current example, it works like this. Consider first the population of students in general. These would be all the students that take the professor's course and take the final exam, but that don't participate in the special training program. As shown in the figure, the professor knows, because of many semesters of collecting data, that the exam scores are normally distributed with a mean of 80 and a standard deviation of 7. That's very useful information because what that also tells us is that in this population of students, the chance of a student getting an exam score higher than, say, a 97 would only be about 2%. And we know that because of the properties of the normal curve. Recall from the previous lecture that approximately 2% of scores in a normal distribution are higher than a z-score of positive 2, which we see that an exam score of 97 is equivalent to a z-score of 2. So therefore, we could say that scoring a 97 or higher is highly unlikely in this kind of regular population of students. But let's think about, we're doing this study, and what happens when our one randomly selected student that attends the training does score above a 97? Let's imagine for a moment that the training program actually has no effect on this particular student's final exam score. In other words, let's imagine for a moment that the training doesn't work at all. Well, if that's the case and the training program doesn't actually work, our randomly selected student's exam score, we would expect it to be similar to the exam scores of the rest of the students that don't participate in the training. That is, if the training doesn't work at all, the randomly selected student is most likely to have an exam score somewhere in the middle or close to average. Remember that that height of the curve tells us what is likely. So if the training doesn't work at all, it would be highly unlikely. We could say approximately a 2% chance that this particular student that we selected at random would score a 97 or higher. So if the student in our study does in fact score above a 97, we would reject the idea that the training program has no effect. And if we reject the idea that the training program has no effect, we must conclude that the training does work. Using the same reasoning, if a student scores above a 97, we would reject the idea that they come from the population of students, like our general population of students, with a mean score of 80. So we would conclude that students who participate in the training program will, on average, score higher on the exam than the regular or untrained group of students. So, in this example, this example follows the core logic of hypothesis testing. In this example, the professor first identified what would have to happen for him to conclude that the training program had its intended effect. That's true of the hypothesis testing process in general. A researcher has to first ask what needs to happen in their study to determine that whatever they are interested in has an effect. Now, I'm going to use the term treatment as a generic way to refer to something that the researcher is interested in. Sometimes the treatment actually is a treatment, like it could be a therapy or it could be a medical procedure. But I'll also use the term generically to refer to anything that one group of people are given or exposed to, like the training in this case. We could say that the training that the student gets is a treatment. Okay? But it could be a particular condition of an experiment, even the passage of time. So in general, the researcher asks the question, what would I need to observe to conclude that the treatment, whatever it is, has an effect? We have to ask, what is the hypothesized effect of the treatment, and therefore what needs to happen? Having determined in advance what we're looking for, the researcher conducts the study. In the case of our example, that was just selecting the random student and then sending them to the training program and then waiting to see how that student performed on the exam. Because it was specified in advance which exam scores from the regular students were likely and which were unlikely, once it was observed that a student, say, got a 97, it was possible to conclude that it was unlikely that the training had no effect, and therefore it was likely that the training had an effect. And that's true for how the process works in general. If the result is unlikely, assuming that the treatment didn't work, it is concluded that the treatment likely does work. Now, if you find yourself just a little confused at this juncture, you wouldn't be the first statistics student to feel that way. Because inferential statistics and hypothesis testing has a very roundabout reasoning. It's very much kind of opposite of what you would predict. As unintuitive as it might seem, there are some good reasons for why the hypothesis testing process was developed this way. One reason for the way that hypothesis testing is done is that you have to think about what information we typically start with. In the case of the professor, he knew what happened when students don't get the training. So therefore, he knows what the distribution of exam scores look like for untrained students. Notice that the distribution of exam scores for the untrained students is exactly what you would expect if training had absolutely no effect at all. If training has absolutely no effect at all, we would expect for there to be no difference in the exam scores between students that get the extra training and those that don't. So in this regard, the professor knew the likelihood of untrained students getting particular exam scores, and that serves as a basis for comparison. So more generally, researchers have the information to figure out the probability of getting a result if the treatment they're interested in has no effect. that really serves as the basis for concluding then whether the study suggests that there is an effect or if there isn't one. So again, I know the logic here is tough, but if it wasn't done this way, in most cases, you couldn't test hypotheses scientifically at all. So in psychological research, and in really many other sciences as well, social sciences, physical sciences, medicine, researchers will base their conclusions on the question, what is the probability of getting our research results if the opposite of what I'm predicting is true? We usually predict an effect of some kind, right? We start with an effect. For example, we predict that the training will improve the exam scores. However, researchers ultimately decide whether there's an effect by determining what range of scores are likely as well as unlikely if there's no such effect at all, right? So we imagine, what if there's no effect at all? What scores would be likely and which would be unlikely? If it's highly unlikely that we'd get our research results if there's no effect, then the then that would be our basis for rejecting that there's no effect. And if we reject that there's no effect, then we're able to accept our hypothesis that there must be an effect. Okay. So the idea is that if we get a result from our research study that are unlikely, assuming no effect, that's kind of a roundabout way for providing support that there actually is an effect. So let's take a look at our example again, and we'll kind of start over from the beginning. And I'm going to go over each of the steps of hypothesis testing in some detail. In doing so, I'm going to cover some special terminology for hypothesis testing. But most important, I'm going to introduce 5 steps of hypothesis testing that you're going to use for the rest of the course. So the first step in the process is to take the research question and restate it as a research hypothesis as well as a null hypothesis about populations. So our research question in this case was, does the training improve exam performance? And we're going to restate that into a research and a null hypothesis about populations. In general, population 1 consists of people who receive some treatment. It could be a procedure, an experimental treatment. In our example, population 1 would be the students that receive the training. Population 2 is a kind of comparison baseline based on what is already known about people. In this case, it would be what is already known about students that take the course in general and who don't receive the special training. So the research hypothesis is a statement about the predicted relationship between these two populations. Often that there's some difference between the populations or there's some effect of our treatment. This is otherwise known as the alternative hypothesis. It's the alternative hypothesis to the null. The null hypothesis is a statement that is opposite to the research hypothesis. So often the null is that there's no difference, or that there is a difference opposite than that predicted between the two populations. Okay, so in this particular example, this is how we would state the research hypothesis. Sorry, here we go. Remember that the question is, does training improve exam performance? So the first step is to restate the research hypothesis by turning the research question into a statement of prediction. So if the research question is, does training improve exam performance? We just turn that into a statement by saying, training improves exam performance. Now, that's a general statement, and so I've included a couple other sentences to better clarify what the hypothesis is for this particular research study, which is that, on average, students who receive the training score higher on the exam than students who do not receive the training. This can also be stated as the mean of the trained students is higher than the mean of the untrained students. I've also stated the prediction using symbols. Stating hypotheses in symbols will be the preferred way of expressing hypotheses in this class. A common way to symbolize the research hypothesis is H sub A. The A stands for alternative because, as I mentioned before, another name for the research hypothesis is the alternative hypothesis. You may also see the research hypothesis symbolized as H sub 1. I just choose H sub A. We then see the symbol for population mean, which is mu. So what I've expressed here is the relationship. I've expressed the relationship between the two populations as mu1, which represents the training group or the trained students, as being greater than mu2, representing the untrained population. So we can see that the symbols correspond exactly to that third sentence, which is that the mean of the trained students is higher than the mean of the untrained students. And again, just to be very clear, when we say mean, we're very clearly referring to population mean as symbolized by those Greek letters, the two mu's there. Okay, now to state the null hypothesis, we just take the opposite of the research hypothesis. So if the research hypothesis was that training improves performance, the null is simply that training does not improve exam performance. Similarly, we could say that on average, students who receive the training do not perform higher than students that do not receive the training, and that the mean of the trained students is not higher than the mean of the untrained students. In symbols, the null hypothesis is symboled as H sub 0, sometimes also called H sub naught. And then in symbols, we would say that mu1 is less than or equal to mu2. Notice that in order to be the opposite of not higher, we need to take two possibilities into consideration. First, the two population means could be equal. If they're equal, mu1 is not higher than mu2 because it's equal. Mu1 could also be less than mu2. It's not higher than mu2 if it's less. So by writing that mu1 could be less than or equal to mu2, we're stating the exact opposite of the research hypothesis, which is that it's higher. Okay, oops, now my animation kind of messed up here. There we go. All right, so just to lay it all out, the first step is that we're going to restate the research question as a research hypothesis and a null hypothesis. We turn our question, does training improve exam performance, into a statement. That statement will be expressed as symbols and using the inequalities that we've done here. Now, something that I want to point out is that in the textbook, they have you stating the null hypothesis as mu1 equal to mu2. Please don't follow what the textbook does here. They kind of start you off doing that, and it's a little bit imprecise. There's a reason that they do it, but please follow the model that I'm showing you here, which is to state the null as the direct opposite of the research hypothesis. Okay, the second step is to determine the characteristics of the comparison distribution. The overall logic of hypothesis testing involves figuring out the probability of getting a particular result if we assume that the null hypothesis is true. Therefore, you need to know what the situation would be if the null hypothesis was true. In our example, the professor starts out knowing key information about population 2, which is this comparison population of students who don't get the training. We know that the exam scores from this population follow a normal curve with a mean of 80 and a standard deviation of 7. This distribution of scores serves as our comparison distribution. Because the comparison distribution is associated with the null hypothesis of no effect, sometimes I refer to the comparison distribution as the null distribution. In our hypothesis testing process, we're ultimately going to get a score from our research sample, in this case the single student, and then we're going to determine what's the probability of getting a score from that sample that large or that extreme in the comparison distribution. Now, the third step is to determine what's the cutoff score or the critical value on the comparison distribution at which the null hypothesis should be rejected. Okay, so we're looking for a cutoff score or a critical value, which we define as the point on the comparison distribution that, if reached or exceeded by the sample score, would lead us to reject the null hypothesis. In general, psychology researchers use a critical value associated with a score that happens less than 5% of the time, assuming the null hypothesis is true. This is usually written as a probability of p less than 0.05. Sometimes a critical value associated with 1% is used, which is symbolized as p less than 0.01. The 0.05 and 0.01 levels are called the conventional levels of significance because they're widely used in psychology. Oops. Now this is important, and so I've just made a single slide about this. When a sample score is so extreme that it exceeds either the 0.05 or 0.01 level of significance, depending on which is used in the study, researchers reject the null hypothesis, and the result is said to be statistically significant. Okay. In statistics, and for the types of tests that we're doing right now, the critical value is expressed as a z-score. We'll learn other standardized statistics as the class progresses, but right now we're going to use z-scores, which are our standardized scores. That's because we're familiar with the normal distribution in z-scores, so that's what we're using for now. The idea is that ideally, before conducting a study, researchers will set a target against which they will compare their result. Again, the question is, what kind of a result would be extreme enough to convince us to reject the null hypothesis? So let's just say in this particular example, we're going to use the 0.05 level of significance, and that means we're going to reject the null hypothesis as too unlikely if we get a sample result that occurs less than 5% of the time, assuming the null hypothesis is true. Now we know that our comparison distribution of exam scores from the untrained students follows a normal curve. Therefore, we know that we can determine that the top 5% of scores in a normal distribution is associated with the z-score, and we know what z-score that is. It's a z-score of 1.64. This z-score was determined by using the normal curve table. Now, if you need a refresher on how we get this value and how to use the normal curve table, please review the previous lecture. Okay. But the important thing to know is that in a normal distribution and in a normal curve, there's a specific z-score associated with specific probabilities, and the specific z-score that is associated with the top 5% of the distribution is a z-score of 1.64. Now, it's important to point out that we're interested in the top 5% of the comparison distribution because of the hypothesis of this particular study. The hypothesis was that training would improve exam scores. Therefore, we're only interested in that very top tail of the comparison distribution. So we're going to set as our cut score for rejecting the null hypothesis a research result in which the sample's z-score on the comparison distribution would be at or above 1.64. All right, the next step is to determine your sample score on the comparison distribution. In practice, this is done by actually carrying out the study and getting the actual results from your sample. Once we have the results from our sample, we figure out the z-score from that sample's raw score based on the population mean and standard deviation. So here, we're going to kind of, we started over. We're going to pretend that we actually did this. We randomly sample a student. We send them to training. We have them take the final exam. And drum roll, this student got a 93 on the exam. That's the raw score. We need to convert it to a z-score. We do that using the population mean and standard deviation. Here's our z formula. I want you to notice a small change to the z-score formula that we used in the previous lectures. Here, the population symbols have been substituted for the previous sample symbols. So whereas previously we had x minus m, now you can see that we have x minus mu, but it basically means the same thing. We're taking the raw score minus the mean, and then we're dividing by sigma, which is the standard deviation. So it's the same formula, it's just the symbols have been modified to reflect the population parameters. Okay, so in doing that, we get a z-score of 1.86. The very last step is to decide whether to reject the null hypothesis. What we do here is we compare our sample's actual z-score that we got in that last step, step 4, to the critical value or the cutoff z-score that we determined in step 3. So we're going to compare 1.86 to 1.64. Now what we see is that our sample result is more extreme than the critical value. That is, it's further, it's found in the tail of the distribution. It's further along on that number line. What this means is that it is unlikely to occur in the comparison distribution. Specifically, we can say that there is less than a 5% chance that our trained student comes from a population similar to that of the untrained students. Therefore, we reject the null hypothesis. We say that our result is statistically significant. Our data are inconsistent with the null hypothesis, and they're more supportive of the alternative hypothesis, which is that the training improves exam performance. So here's a summary of the 5 steps. We restate the question, the research question, as a research hypothesis and a null hypothesis about populations. We do this using symbols. We then determine the characteristics of the comparison distribution, and specifically we need to determine what is the mean, the standard deviation, and the shape of that comparison distribution. That's typically determined by information that we already have. Next, we're going to determine the cutoff or critical value on the comparison distribution at which the null should be rejected. That cutoff value will be a z-score, which I like to call the z-critical. Next, we'll determine our sample score on the comparison distribution, and we do this by calculating a z-score using the population mean and standard, using the raw score, the population mean, and the population standard deviation. We then determine whether to reject the null hypothesis. We will reject the null hypothesis anytime the z-score from step 4 is more extreme in the hypothesized direction than the critical value. So if we have a positive critical value and we get a positive z-score that is more positive or larger than the critical value, we reject the null. If we have a critical value that is negative, the z-score that we calculate needs to be even more negative than that critical score. So here's how we convey the results of the hypothesis test in a research article, and just some general information for how to interpret the results of a hypothesis test in a research article. Now, this is what it might look like. I do want you to keep in mind, again, this is a very artificial example. We'd never do a study of this kind using a sample of just one person, but I've written it up for how it might appear, which is a way to learn how you might see things in a research article. There's a couple things to look for when reading how statistics are reported. So here's what to look for. The first thing would be an indication of statistical significance. This is typically found at the end of the sentence as it is here. You're going to be looking for something like p less than 0.05 or p less than 0.01. That tells you that the statistical result met those conventional levels of statistical significance. Now, because statistical tests are very often, almost always, calculated using a statistical software, most statistical software programs produce an exact p-value that is associated with the result. That is, the statistical software can tell you what is the probability of obtaining this result if one assumes the null hypothesis of no effect. So very often you might see an exact p-value reported in a research paper. What you need to do is you need to look at that exact p-value and say, is that less than 0.05? Or if it was specified in advance that the other conventional level of 0.01 was being used, is that exact p-value less than 0.01? There should also be some description in the write-up of what happened, that scores increased or decreased, or were higher or were lower. There should be a symbol for the statistical test that was used. In this case, a z-score was used, but you'll see other letters like a lowercase t, an uppercase f, Greek letter beta, Greek letter chi. These are all symbols associated with specific statistical tests that you're going to learn about in this course. And so when you see that particular letter, you'll be able to identify, oh, I know that that was a t-test, or I know that that was an analysis of variance. Finally, there should typically be some descriptive statistics like a mean and a standard deviation, or just a test score like we see here, a 93, so that we're given some descriptive information about the research sample. To wrap up, I want to go over some of the implications of rejecting as well as failing to reject the null hypothesis. So first, when you reject the null hypothesis, all you're saying is that your results support the research hypothesis. We don't say that the results prove the research hypothesis or that the results show that the research hypothesis is true. All we can say is that they support the research hypothesis. This is because terms like prove and true are too strong. This is because research studies and the results of research studies are based on probabilities. Specifically, the results are based on the probability being low. Well, we can say that conclusions are based on the probability being low of getting the result if the null hypothesis is true. Proven and true are fine to use if we're doing like a mathematical proof, but using these words in scientific research is not acceptable. It's okay, or it would be fine when speaking hypothetically. So, like, for example, if this hypothesis were true, then this is what I would expect. But not when we speak about conclusions of about an actual result. So what you can say when you reject the null hypothesis is that the results are statistically significant and that the results support or provide evidence for or in favor of the research hypothesis. Never use prove, just say supportive or provide evidence for. Okay, when we fail to reject the null hypothesis, the result is not statistically significant. However, we also don't say that the result would prove the null hypothesis or that the null is true. What we do is say that the result is not conclusive. The idea is that the results may not be extreme enough to reject the null hypothesis, but that doesn't mean that the null hypothesis is necessarily true. Let's just say, for example, that the training program had a real effect, improved exam scores, but it was only a small effect. In that case, we wouldn't expect our student to maybe have an exam score that was much higher than the other students. Therefore, we would not have been able to reject the null even though it was false. So, showing that the null hypothesis is true means you would actually have to show that there's no difference between the two populations. That's a very difficult thing to do because with research, we typically never have populations. We only have samples. It's always possible that there is a difference between populations, but it's just a small difference. And therefore, it can be challenging to detect that small difference with a research sample. Therefore, again, if the result is not extreme enough to reject the null hypothesis, we just say that the results are inconclusive. This is an idea that I'll return to later in the course, but really for the time being, and after listening to this lecture, mostly I hope you have an appreciation for the core logic of hypothesis testing and a basic familiarity with the 5-step hypothesis testing process. If you aren't feeling particularly comfortable with the process right now, that's okay. In the next lecture and throughout several of the lectures that come, you're going to get a lot more practice in the 5-step process. I would say, though, if the core logic isn't very clear, it is probably worth reviewing the corresponding sections in the textbook, as well as rewatching some of the earlier parts of this lecture that went over that core logic, because that is the foundation of the process, and we're going to be doing hypothesis testing for the remainder of the course, so it's good to feel confident in it.